So our second speaker is Danny Tarlow from Microsoft Research. Danny got his PhD with Rich Zemmel at the University of Toronto, where he also interacted with the same Jeff Hinton. And he was a postdoc and now a researcher at Microsoft Research in Cambridge. And he's going to tell us about A-star sampling, and I would add that this work received one of the best paper awards at this year's NIPS conference. So please join me in welcoming Danny Tarlow.
All right, great, thank you. The one other connection to Jeff Hinton here, since this is the theme, is the student here. The student collaborating with us here, Chris Madison, is one of Jeff's students in Toronto. And then I'll say this is also work with Tom Minka, who's a fellow researcher at Microsoft. Okay, so to motivate this work, I want to start off just looking at the broader picture a little bit. You've probably, most of you hopefully have heard of this term probabilistic programming. And this basic idea is at least the sort of motivation behind where we're going to go here. So the idea of probabilistic programming, if you haven't seen it before, is what we'd like to do. This is, sorry. There we go. What we'd like to be able to do is we'd like to have the programming languages that we all know and use and love, but we'd like to augment them with a few additional things. So what we'd like to do is we'd like to augment them with the ability to add uncertainty. So how does this actually work? What happens is, instead of assigning values to all of your variables, what you do is you add into your programming language random number generators from particular distributions. So what the example here is, I should probably start by saying this is meant to be partially a joke, but it came up when I was getting my hair cut, and the barber was telling me that a bunch of lawyers would come into the barber shop, and then they would have to leave at 5:30, or they would finish up at 5:30, but they would all say that they were going back to work because they needed to be the last one in the office. And it was very important in the office politics that they left after their boss left. So thinking about that, let's try to build a simple program that helps these lawyers out. Okay, so the way that it'll work is what we're going to basically do is we're going to build this simple model of when the boss is going to leave. And we're going to have this programming language which has these random number generators in it, which basically allow us to say, I don't know what the value is going to be, but I have some uncertainty. I have some prior distribution over what I think it's going to be. So how would this look? Well, what we're going to model here is we're going to have a distribution over when the boss gets into work and how many hours in a day that the boss works. And then we're going to have some parameters here. Don't worry about what they are, A, B, C, and D. These will control some gamma distribution, say. And then we're going to say that the gamma distributions have some shape that is given by these parameters. And then what's going to happen is that each day we're going to say that the arrival hour of the boss is drawn as a sample from this arrival distribution. The number of hours that they're going to work is going to be a sample from this hours worked distribution. And then the hour at which the boss departs is some deterministic function here. It's just the arrival hour plus how long they worked. Okay, so this is a very simple model. And then what we're going to do next is we're going to say instantiate this model, and then we have these extra constructs in the programming language which are observations. And we're going to be able to say that, well, we know that on January 27th we saw that the boss arrived, say, at 9. We saw it on the same day the boss left at whatever that time would be. And then maybe the next day we don't know when the boss arrived, but we're able to observe what time he left. And then maybe we're on January 27th, we know the boss arrived at 10, and then what we want to know is we want to know what's the best time to leave at the end of this day. Okay? So how is this going to work? Well, we've constructed a model up here. We've added these observation statements which are conditioning on things that we've observed in the world. And then the third part is this infer statement. And so what this is going to do is we're going to be able to give it some expression here, and what it's going to do is give us a probability back. So in this case, we're saying infer what is the probability that the departure hour at a particular day is less than some hour that we give. So, you know, at this time, what's the probability that my boss is still here? Or sorry, that my boss has already left. And then you can imagine adding some decision theory on top of this, and you can call this function in different ways, and you can construct a function which says, for any particular day, what is the optimal time for me to leave. Okay?
I'm sure this is not important, but this is my time to leave or the boss's time to leave?
This is my time to leave. This is when should I leave. Yeah. Right, so you can imagine, having this spin when you see your boss arrive or leave, you punch something into your spreadsheet or whatever it is, and then you run this program each day and it tells you what time to leave. Okay? So the idea of probabilistic programming is the user is the programmer, just specifies this, and then from that specification, like we saw in the previous page, there will be an inference engine underneath the hood that turns the crank and does all of the computation for you. Okay? So the programmer doesn't have to know about the details of probabilistic inference. They just have to understand what it means to write down this model. And then there is this magical engine underneath the hood that will give you back answers. So this is just a sort of a schematic diagram of what I walked through in the previous page. Basic idea is you construct a model, you have some observations. The details vary from engine to engine, but there's a lot of these out there now. One of them, this one is infer.net, which is developed at my lab. And then the output is going to be the results of all of the infer statements that you sprinkle in here. Okay, and these outputs could be approximate marginal probabilities. They could be samples. It doesn't particularly matter. Different engines will have different ways of dealing with this. But in this case, let's imagine them as being samples from the model. Okay, so this is the sort of task that we're thinking about, and I'm just going to abstract this a little bit and make it a bit simpler, but this covers in the full generality what we'll need to be able to do inside these inference engines. The basic idea is we're given some function. Think of it as a log probability distribution function that incorporates all of the observations that we've had so far. And what we'd like to do is we'd like to exponentiate, normalize this guy, get a probability distribution, and then draw a sample from it. Okay? Okay, so supposing we have this inference engine, we write the model down. This all seems great so far. We go, we post this online, put it on GitHub. And now the idea is that everybody in the world can use this, and the world is a better place for having done this. Okay, there's a big problem with the way that current systems work, and that's sort of the motivation behind what we're going to do here. So if you look at the README that needs to go inside this boss model, based on the current state of affairs with all of these probabilistic programming engines that are out there, you need to say this thing, sometimes it'll work and sometimes it won't work. What's more is that when it doesn't work, it still is going to output an answer. And there's no way to tell if this answer is good or if this answer is bad. And really, it could be arbitrarily bad. And so, there's a lot of effort taking, for example, infer.net at Microsoft and Cambridge. People have spent about 10 years trying to develop this. Some serious effort has gone into this, but still, there isn't a notion of, I've given you the right answer and I can prove it. Okay? So, there's trade-offs here. Obviously, it's a hard computational problem in the worst case. You're never going to be able to prove ahead of time that you're able to solve this. But if you just think about this from what is trying to be achieved with probabilistic programming versus what is the technology offering, to me, there's this huge clash here. This just, imagine what happens if you try to use this. The thing fails. It tells you, I'm sure your boss is gone, but in fact, he's not. Okay, so right. So the proposal, the thing that I want to say is the aim that we should strive for, which is a compromise between what's possible to compute and what would be useful in this more general setting, is we still make this assumption that sometimes it will work and sometimes it won't work. I think we're never going to be able to avoid that without putting huge restrictions on what types of models we're able to express. But all that I want to say is when it doesn't work, it'll tell you it doesn't work. Okay? And so then you can imagine inside your program, it throws an exception, and then you can resort to some fallback reasoning. So in the boss example, I am told that the inference didn't work for whatever reason, and I know just to stay late if I want to be safe. I can fall back to some other way of making decisions. Okay, so let's look at the inference algorithms in a bit more detail, what's out there. So what we'd like to do is we'd like to have inference algorithms that draw samples from probability distributions and guarantee some form of exactness in this way that I'm saying in the previous slide, which is it may run forever, but at least if it does run and it gives you an answer, you know the answer is correct. Okay, so there's two traditional classes of how to do this. So one of them is based on Markov chain Monte Carlo, and there's this idea called coupling from the past. What it basically says is it allows you to simulate Markov chains starting from all possible starting positions, and then you keep running them until you prove that all of those chains have coalesced into a single configuration. And then at this point, you can guarantee that you have an exact sample. And then the other approach is based on rejection sampling, where you draw proposals from some simpler proposal distribution, and then you compute a test, a random test, to check whether you should accept this sample or not. And if this test tells you to accept, you know you've gotten the right answer. Okay, so what I want to add here is there's a different way of thinking about this problem, and that's what I'm going to tell you about today. Okay, and so the starting point is this sort of simple probability trick that's kind of cute, but not very practical, it seems. But we're going to take this, and then we're going to develop into sort of a bigger sampling algorithm. Okay, so I'll start by telling you about that. Here's the basic idea of how the technical part will go. The first thing that I'll do is I'll tell you about what is this Gumbel max trick. Then I'll talk about the Gumbel max trick is for simple discrete distributions with a small set of possible options. And I'll show how to generalize this to continuous distributions or exponentially large discrete spaces if you're interested. And then I'll talk through the details of sort of what are the necessary pieces here, and then finally present the algorithm at the end. Okay, so let's talk about the Gumbel max trick. But first, what I want to do is tell you a bit about this probability distribution, which is called the Gumbel distribution. It comes from extreme value statistics, but it has some really interesting properties. But first off, what is it? You know, it looks kind of like most other distributions you've seen before. It's got a heavier tail on the upside. So if you draw samples from this, you're more likely to get really large values, and you're less likely to get small values. And the PDF for this is this double exponential form. The CDF looks something just like having this exponential form here, or double exponential form. And then just a practical point, if you want to sample a Gumbel, it has a location parameter for our purposes here, which is m. If you want to sample a Gumbel with this location value, what you do is you generate a uniform number using rand, and then you take the negative log of the negative log of the uniform distribution, and then add the location parameter to it. Okay, so this has some interesting properties, this distribution. It's something that's called max stable. So you might know the Gaussian distribution, if you take the sum of two Gaussian random variables, which you'll get back as a Gaussian. So it's sort of, it stays closed under addition. The Gumbel distribution is closed under maximization. So it's sort of the max analog in this setting. So a bit more specifically, let's just say that you have two Gumbel values, G1 and G2, drawn from a Gumbel with location 0. Then the max of these two is going to be distributed as Gumbel with location equal to log 2. And so I'll even prove this one for you. So the point of this is just to show that these properties arise from simple manipulation of the probability density function. So we want to define this random variable z, which is the max of G1 and G2. What's the probability that z is less than some value g? Well, it's just the product of the probabilities that each of the original variables were less than this value. Then we take the CDFs of the Gumbel distribution, multiply them together. So this is the CDF of one Gumbel, this is the CDF of another Gumbel. You can then combine these together and get two of those. And then all we're going to do is try to move this 2 to be inside this exponent. So we take the exp of a log, and then we move this inside. and then we get an x of a negative x of log 2 in here, and then this is the location parameter of the Gumbel, and so this is a Gumbel with log 2. Okay, another really interesting property that Gumbel distributions have is if you look at what is the probability that one Gumbel drawn variable is the argmax amongst a set of Gumbel random variables, then it behaves like a softmax. So if we have, again, if we now have a Gumbel drawn with location equal to phi 1, another Gumbel with location equal to phi 2, then the probability that the first Gumbel is bigger than the second one is this familiar expression you've probably seen before, which is the softmax. I won't prove this one, but it follows in the same way. You can sort of write down the expression for what it is, that it's the argmax, compute an integral, and you get back this. Okay, so there's one more sort of more general version of this, which is not so hard to see given what I've told you so far. And that is, now let's suppose that we have a set of variables, more than 2 of them, that are drawn independently in Gumbel distributed, and each one has, okay, so each of these GIs is going to be a Gumbel with location 0, and then we want to know what is the distribution of the argmax over any subset of these indices B, and this is going to be the softmax restricted to the elements that are inside the subset. This just follows from what I told you before. And similarly, the max within any subset is going to be distributed as a log sum x, a Gumbel with location equal to log sum x of the elements of the subset. Okay, and then last property of the Gumbel distribution is I've told you what are the distributions of the max and what are the distributions of the argmax. It turns out also that these quantities are independent. So that is to say that if I wanted to have a subset of these random variables that were Gumbel distributed with some location, and I wanted to know what was the max and what was the argmax of this set, I could actually just sample these separately from these 2 distributions. So I could say, okay, first I'm going to choose the argmax according to a softmax distribution, and then I'm going to choose the max as a Gumbel with location equal to the log sum x of the quantities that went into it. And these don't have to communicate. So this is just a plot to show you here. For example, I just simulated here 3 different phi values here and said, what's the probability of the value of the max given that the argmax was equal to 0, probability of the max given that the argmax was equal to 1, probability of the max given that the argmax was equal to 2. And so these location parameters were different, but the distribution over the max given that you chose one of these to be the argmax does not change. Okay, so what is the Gumbel max trick? Now it seems quite trivial given that we know all of this stuff, but so the problem description is we're given these phi's, which you can think of as negative energies or unnormalized log probabilities. And what we'd like to do is we'd like to sample from this softmax distribution where we exponentiate these guys, normalize, and then sample from that distribution. The Gumbel max trick has 2 steps. You say for each of those elements I, you generate a random Gumbel variable with location 0. And then all you're going to do is return the argmax of the phi value plus the Gumbel random variable that you've drawn. And this will give you an exact sample from the softmax distribution. Okay? And people call this the Gumbel max trick. Okay, so now let's think about continuous distributions. So far I've said you have a set of k independent Gumbel random variables. You can see how you can use this to sample from these simple discrete distributions. Now what happens if we want to use the same idea, but we want to sample from continuous distributions? So the sort of first questions to ask here are, what does it mean to perturb space? So we can think of, in the discrete case, we had these values phi for each of the discrete values, 1 through k, and we then added this perturbation, which was this Gumbel noise on top of them, and then this system had the property that the argmax was a sample from the distribution that we cared about. So if we think about continuous space, what needs to happen is we're going to have a continuous function, which is a log unnormalized probability density function, and then we're going to, in some sense, add independent perturbations to each point in space, and then we're going to ask, what does this mean, and how do we work with this object? And then the second thing is, once we've shown that such an object makes sense to think about, how do you actually perform this maximization to find the argmax of this perturbed function? Okay, so just to sort of make it clear, the setting we're in now, we basically have the same idea. We're given this phi, but now phi is a function over continuous space, and it can take a vector of real values, and then we want to sample from the same Gibbs distribution here. Okay, so what are the analogs that we want? It turns out the analog that is useful for us to think about is to take this last property that I told you about what was the distribution of the max and the argmax in any subset. And so let's think about what that would mean in continuous space. So this is just this set of equations that I showed you before. It says that the argmax in any subset is distributed as softmax restricted to that subset, and the distribution of the max is, oops, this should say Gumbel here, with a Gumbel with location equal to log sum x of this. So all we're going to do here is we're going to replace the sums with integrals. So what we would like is we would like that the argmax is distributed as the Gibbs distribution, this restricted to be within the subset. And then we would like the max to be distributed as, this should say Gumbel again, with location equal to the log integral of the exponentiated density function within this region. Okay. And so, right, so then we did a little bit of looking around in the statistics literature and whatnot, and we found such an object. So there's this master's thesis, which has the definition of sort of a more general structure than this. They call them max fields. But so we specialize this to deal with Gumbels, and when the specialization deals with Gumbels, we're calling it a Gumbel process. And so this is the sort of continuous analog of the object that we want to think about. Sorry, I think I used a macro for Gumbel and didn't realize that it wasn't working. Okay, so what is a Gumbel process? So we're going to be given this measure, which is just going to say, we're given some region B, and we want to return what is the measure of this region. This is going to be the integral of the exponentiated phi function that I was telling you about before. And then we're going to say that we're defining a random variable for each region of space B. And then the Gumbel process is going to be a collection of these random variables for each measurable subset if these three properties hold. So the first one is the marginal distribution, that for every subset, the marginal distribution over a subset of the max is distributed as Gumbel with log measure of that region. The independence of disjoint sets, which says if you have two independent subsets, the distribution of their max is independent. And then finally, there's this consistency constraint, which just says that if you have a random variable for subset A, a random variable for subset B, then the random variable assigned to the union of these spaces needs to be equal to the max over the random variable assigned to each of these component subsets. So this just says, you know, you can think of it as it's consistently assigning values to all regions of space, and it's, if you take any subset and look at the max, it's not going to contradict what you've looked at somewhere else. Okay, so maybe sort of as an example to think about, let's go back to this discrete case. What is a Gumbel process for this case where we just have discrete variables 1 through k? The Gumbel process is just going to be the distribution assigned to all subsets of those random variables. So we can construct, we could actually instantiate this whole Gumbel process in the discrete case by saying, let's sample the Gumbel value for each of the base components. And then what we're going to have is, in order to construct the value of any subset, we're just going to take the max over the values that we've sampled for the base components of the subset. Okay.
If you take the analogy with the Gaussian process, finite subset for a multivariate Gaussian.
Mm-hmm.
And their analogous definition, can't you say it's something? The Gumbel process is only finite subset, product of Ising and Gumbel, is that not?
So we're modeling it more as a Poisson process type thing. So in the Poisson process, you're assigning these counts to each region. And so it's sort of the analog here is you're assigning a max to each region. Not sure about the Gaussian process case. Okay, hopefully that's clear enough. Is there any questions at this point? Okay. So now we have this mathematical object. Let's think about how can we actually construct it, or how can we usefully generate samples from it. Well, by analogy to the discrete case, what you might think to do is let's do it in what we call a bottom-up manner, which is to say, first instantiate the perturbations for all points in space, and then from those deterministically construct the value for all subsets. Yeah, it sort of makes sense. It's okay to think of that intuitively, but you'll never be able to execute this because the first step is generate infinitely many random variables. So the way we're going to go about doing this instead, the idea here is that, well, we don't need to instantiate all of these random variables. Let's think about instead just instantiating the largest ones first. And so what do I mean by this? I mean, let's start generating values by saying let's first generate the location and the Gumbel value for the maximum across all of space. And then conditional upon that, let's divide up space somehow and say let's sample the largest value and the location of that largest value in this region, conditional upon having already drawn the largest value over all of space. And then let's recursively divide up space and proceed in doing this. So let me show this in pictures. So what we're trying to do is we're trying to generate, in some sense, the largest values and their locations from this Gumbel process. So what we're going to do is we're going to first pick the point in space that is assigned the largest value. But what I told you from the definition of the Gumbel process is we actually know what the distribution of this thing is, right? I told you what is the distribution of the max and what is the distribution of the argmax. And these are just distributed according to the Gibbs distribution equations I showed you before. So you can say the value of the largest Gumbel is just going to be a Gumbel with location equal to the log measure of all of space. And then the x value, the x value is just drawn according to the Gibbs distribution, and then the value associated with it is drawn according to a Gumbel with this. And then we can think of this as we've instantiated these infinitely many random variables, and we've looked for where was the largest one and what was its value, and that's this guy. So now what we need to do is we need to recurse. So what we're going to do is we're going to split space up. We'll choose to divide it into B and B complement. So we'll remove this one point from space, and then we'll say, now let's look at just this region here to the left. Now, we know what is the distribution marginally of the largest value, the largest location in this region of space B, and that's just going to be distributed according to this Gibbs distribution, restricted to be in the subset. And then the value that it's going to have, you can work it out, is it's not quite a Gumbel distribution, but it's a Gumbel distribution truncated to be no larger than the value that you've drawn already before. So what this allows us to do is say, okay, we've drawn the largest value in all of space. Now let's look at some different region of space B, and let's draw the largest value in this region of space and its location. Okay? And then what we can do is we can continue this. We can divide up space. It always is of the form that we're going to draw the location from a Gibbs distribution restricted to some region of space, and the actual value associated with a point is going to be a truncated Gumbel. Okay, so we now have the ability to do somewhat reasonable computation. We don't have to generate infinitely many random variables. We haven't really gained anything at this point. So let's just yeah, let's look at this slide. So, yeah.
So if you repeat this very, very long, then this instantiation over all of X looks like a horrible fractal distribution.
Yes.
Is this what we should expect?
Yeah. There's the independent subsets have independent values, right? So you could think of this, you could think of generating things in the bottom-up way, where you divide space up into as many tiny little regions as you want, and you draw independent random variables for each region of space to be the max in that region. And so there's no smoothness or anything like that.
If you would like to say, I want to find the distribution, so like draw a Gaussian process, from a Gaussian process and find the maximum, which is something that's maybe useful for Bayesian optimization.
Mm-hmm.
You would then expect smoothness. So you would expect the next largest to be very close to the largest. Would it still work? Is it significantly close?
So the definition of a Gumbel process will necessarily not be smooth. So, okay. Right, so to recap where we're at. So we started off saying we're trying to sample from these probability distributions, and we said, okay, let's think about a strange object, which the optimum of this is a sample from the distribution that we care about. But then when I've just told you about how to actually work with this, the first step was sample from the distribution that we cared about. Okay, so we haven't gained anything here. We've just said, here's a different way of thinking about what's going on, but we haven't gained anything from a computational perspective. So the next step, the way to make this actually do something is what I'm going to tell you about now. And the inspiration is going to come from proposal distributions in rejection sampling. Okay, so we were given this phi function, which is our log probability density function we care about. What we're going to do is we're going to split it up into a sum of two components. One of them we're calling I because you need to be able to integrate it attractively, and O because you need to optimize or upper bound it attractively. But what we're going to do is we're going to pull out some part that we know how to work with analytically, and then there's going to be some remainder part that we're going to need to be able to compute upper bounds on. Right, and so what we're going to require is that we can instantiate this process that I just told you before for the I component. So we need to be able to compute these log volumes that I was telling you about and sample from restricted regions of space. Okay, so I'll just tell you the steps here. So let's think about a different Gumbel process now, where the measure is based on just the tractable, just the proposal part of this, the part that we're able to integrate. We can now run this procedure that I told you about, where we start by generating the maximum and then we recursively divide up space and generate the maximums within regions, just for this I part. And what we'll get is we'll get this stream of values, which are the Gumbel values, and the locations at which they occur. And then the key thing that, I'm not going to prove it, but the key property that comes out here is what we can do is we can come in, we can take these values, and we can look at what is the leftover part at the locations that we've drawn. And if we go and we add that to the Gumbel values, then what we get back is we get something that is like a Gumbel process for the original distribution that we cared about. It's just these points are not necessarily in any sort of sorted order anymore, because these O's can potentially change what is the ordering of the values. Okay, so here's an attempt to explain this in pictures. So this is what we started off caring about. This is a Gumbel process distributed according to this full phi function that we cared about. This was the tractable Gumbel process that we instantiated just from the I component of this, and we said that we know how to generate these spikes for different regions of space from this I1. And then what we can do is we can come for each point in space, compute this is the O function. This was the part that we left over. Say it looks like this gray line. And we can come and we can move these according to the I. So this length here is meant to be equivalent to this length here. This length here is meant to be equivalent to this length here. And all we've done is we've added O of x to all of the values that we got out here. And so you can see this, that this was the largest value in the original Gumbel process. Once we come in and we add these O's, it might rearrange things. So now this becomes the largest value. And then what I just told you is that these two things are equivalent in the distribution that they impose. Okay, so we can think of a Gumbel process in both ways, and it's going to be, thinking about it this way is going to make the optimization make some sense. Okay, so now we're ready to tell you about the algorithm. The algorithm that we're going to use here is going to be A-star search. So A-star search is this algorithm from heuristic search. I don't know when it came out, the 60s maybe. And what we're trying to do is we're trying to search over space for the maximum of this Gumbel process. And we're going to do it by guiding the regions that we explore according to some upper bound. So we're going to have this upper bound that says, for each region of space, what's the largest value that we could possibly find here? And then we're going to explore that region. In doing this, we're going to divide up space further, compute new upper bounds, and we're going to keep doing the search until we have provably found the maximum of this thing. Okay, so where does the upper bound come from? I told you from the last slide, this is the tractable samples from the samples from the tractable Gumbel process, and then we have this O function that we're adding. And so the objective that we have is the sum of these two terms. And what we're going to do is we're going to use this bound where the maximum of the sum over some region of space is going to be bounded by the sum of the maximum of the two terms. Okay, so there's the component here, which is just now the Gumbel values from the tractable part, and then a term here which is just a function of this leftover part. Okay, and then the reason for doing this is these are both easy to compute. So the maximum value of a Gumbel from the tractable part in a region is just that value that we've sampled associated with the original Gumbel process. And then in order to compute an upper bound on this O function for some region of space, we resort to all of the methods people know about in machine learning, where you use convexity or you use, there are interval methods. There's various ways of coming up with bounds on functions. We're quite good at that. Okay, so let's see an execution of how this is going to work. So here's this O function, and then what we're going to do is we're going to start off by drawing the location and the Gumbel value for the maximum in the tractable Gumbel process. So this is the largest noise value for the I part. And then what we're going to do is from here we can compute an upper bound. So the upper bound is going to be this guy, this length here, which is the maximum of the noise part, plus some upper bound over the O function over all of space. So we need to implement this somehow. But once we've done that, then we can compute this global upper bound. Then what we're going to do is we're going to remove this point from consideration, split up space into two parts, recompute the upper bounds for both regions. So these guys are the new upper bounds. And we've also now drawn the maximum noise part for each of these regions, conditional upon having drawn this part. And now A star tells us that we should look for the region with largest upper bound, which is here. And then we're going to explore this region. And so how's that going to work? Well, we're going to compute a lower bound, which is the O function plus this noise part. And then, right. So this is a bit out of order, but that's how the upper bound was computed. It's just what I said before. It's the noise part plus we now have some method to bound the O function, but only in this region of space. So we might be able to improve our bounds by restricting attention just to some subregion. And now what we're going to do is we're going to split up space again. In each of these regions of space, we're going to draw what is the largest noise part. So this guy in this part, this guy in this part, recompute the upper bounds. And now what we can see is that we have a point here which has a function value of the O plus the I, which is greater than the upper bound over all the rest of space. And so at this point, we've proved that we've found the global maximum of the Gumbel process that we cared about. And this is an exact sample from the distribution of interest. Okay. Right. Here's the actual algorithm. I think we don't need to go through it. The point is just that there is a priority queue. It's going to have priorities, which are things like the sums of the G is the Gumbel values, the M's are the bounds in regions of space. It's really not that hard to implement. It's you just have to write your functions that compute these bounds and that draw the samples and compute the volumes. And then from there, it's like any other search that you learn about in your first AI course. Okay, just to lay out there, what are the components that you need? So you have to define this initial region, which could potentially have an infinite extent. You need a strategy for splitting up space. So here it was just sort of regions of space. In general, we've just been playing with hyperrectangles, but maybe you could do something more interesting. You need a function that's able to sample from the proposal distribution restricted to any region that you're going to encounter in your search. You need a function that computes the volume of the exponential of the proposal for any region of space. And then you need to be able to compute these upper bounds. And that's about it. And then from this, you can run this algorithm and you'll get an exact sample. Oh, right. It also works in the discrete setting. So for example, if you wanted to use this for Ising models, you could say that your initial region is now a product space of n binary variables. A function that divides up space, you might condition on each possible value of a random dimension that you haven't looked at before. Your proposal distribution might be a tree structured distribution where you can use some product to sample and compute partition functions. And then for your upper bounds, you can use your favorite upper bounding technique from discrete map inference. So you can use linear program bounds or anything else that you like. Okay. How am I doing on time? 15? Okay. So maybe I'll say, I think I'll skip this part, but I'll sort of say quickly, there is a close connection to rejection sampling, if you know this. One result is that if you use plain old rejection sampling where you have the same proposal distribution that you're using throughout all of your proposals and you just keep using it until you find a sample to accept, that's equivalent to a very bad version of A-star sampling where you start with some upper bound on this O function and then you never refine it as you continue to search through the tree. And so we can show that you have exactly the same runtime as rejection sampling in this case. When you do refine the bounds, there is another algorithm called OS star, which uses exactly the same components. It uses these upper bounds over regions of space, and it uses the same style of proposal distribution where you first choose a region and then you choose a point within that region to propose. And there is a close relationship to this algorithm as well, except it's not equivalent, and A-star sampling actually gives you something that's more efficient than this algorithm. So there's some subtleties about exactly how the randomness is used that makes it work a bit better. I'm going to skip this detailed comparison between the two algorithms, but I can tell you more about this after if you're interested. Right, the end takeaway is that this OSR algorithm looks exactly the same. You implement exactly the same functions, but we get something that's moderately more efficient in the sense that this OS star algorithm tends to use 20 to 40% more computation than A-star sampling. Okay, so let me just show you a couple experiments. Okay, the first thing that we did is we looked at probably the simplest problem you can think about, which is estimating the mean of a Gaussian from n observations. So how does this look? The proposal distribution is just a prior, so this is the unnormalized log PDF of a zero mean Gaussian prior. The observations here are xi stars, and so this O is going to be the sum of the contributions from each data point that we've seen. And then we play around with different bound functions. So what we're looking at here is what are the different strategies for computing these bounds and how does this affect the performance of the algorithm. So this UI function can be filled in 3 different ways. What we're going to do, if we have a constant bound, we're just going to say for each point I independently, let's look what is the maximum value of this term inside a region here, which is just saying, so we have this quadratic, it's bounded in some region, and we just say what is the maximum value there, and then we're going to add all of these up to get these, what we call constant bounds. Linear bounds, what we do is we say in a region, let's look at the maximum value in a region and put a linear upper bound on this quadratic there, and then let's say that our total bound is the sum, it's optimizing over the linear function, which is the sum of linear bounds at each data point. And then the quadratic bound here is just computing the exact upper bound of this function. And the basic takeaway here is that here's the number of data points that you have. The blue is, so this is, let's just look at, say, how many bound evaluations you need. That's the solid lines. The growth here is, it looks like it's somehow polynomial in the suboptimality of these bounds, which is actually a lot better than rejection sampling-based approaches. You pay a lot worse in the suboptimality of bounds. Another thing we looked at is this comparison between OS star, and so here we have a Bayesian regression setting where we have a heavy-tailed noise model, which gives us back this problem where we have a multimodal posterior and we're trying to sample the weights. And what we've done here is we've taken 2 versions of this OS star algorithm. This is the square and the diamond. And we've also added this additional parameter that allows us to trade off how many bound evaluations we need to use and how many likelihood evaluations or O evaluations that we need to use. And what you see is you can sort of move around here. The x-axis is how much cost we spend on the likelihood evaluations. The y-axis is how much we spend on bound evaluations. These red lines are sort of equi-computational cost. And what you see here is that there's this regime at which A star operates, which is better and dominates this rejection sampling-based stuff, or adaptive rejection sampling-based algorithms. And then just very quickly, to return to this probabilistic programming setting, we looked at, can we use this in a more generic setup? So we went online and we found this branch and bound library, which had implemented this method where you give it a symbolic expression that describes your PDF function, and then it will give you upper bounds for this function. And then we can use this to have nonlinear regression, to do nonlinear regression in many different settings. So this is saying that the model is y is equal to parameter a times some function x is your input, and then you have these other parameters. So a through f are the parameters of your model. And it's very easy to just plug this in. So this required no problem-specific code here. It's just the user could write down this symbolic expression, and then what we're able to get back is exact samples. Okay, so I think I'll just wrap up there, saying that, so just to recap, we've taken this Gumbel max trick. We've said, what happens in continuous space? Can we think about a sampling algorithm based on that? And it actually gives both a new way of thinking about the sampling problem and an algorithm that seems to be more efficient than the alternative, the sort of the most closely matched comparative. Okay, so then I'll just leave here the sort of ideas looking forward. I'll take questions.
You mentioned the story with the motivation, where a probabilistic program could fail and you wouldn't know that it failed. So this is a perfect sampling thing. So if it succeeds, it succeeds. But you could take forever, right?
Mm-hmm.
So how do you, could you sort of connect this back to the original problem?
Yeah, sorry. Right, so I imagine this works by you set a timeout. So this algorithm runs for 1 minute. If it hasn't found an answer, then it just returns, I failed. So maybe the question here relates to what distribution are you sampling from if you stop early? And so we've looked at this, but so you can run this algorithm and you can say, I found some lower bound which has improved over the course of running this algorithm. And if I haven't proved that it's optimal, but I just return it, what's happening? And we see this qualitative behavior that the longer you run it, it sort of moves smoothly towards the distribution that we're interested in, but we haven't been able to analyze exactly what this means. So that's a question. I'm not sure what the answer is.
So how does it scale to higher dimensions? So
Ah.
it's a relatively small
Yes.
problem?
So it scales quite poorly in the dimension. So you can come up with simple examples like if I'm trying to sample uniformly from a hypersphere and I have hyperrectangular bounding regions, then you do no better in this case than just plain old rejection sampling, which is exponentially bad in the dimension. And that's just because sort of it's this geometry of high dimensional spheres where if you try to carve up space with rectangles, then there will pretty much always be some part of the sphere inside the rectangle, but it would always be exceedingly small amount of the rectangle that has any sphere inside of it. And so this means that you can't improve the bounds. The bounds don't help you because the upper bound of your function within some region is actually it's high. But if you were trying to hit this with your proposal distribution, you're never going to hit it. So what's going to happen is your bounds are going to basically stay the same throughout all of this. You're going to generate a bunch of locations. They're all going to have really bad lower bounds, and you're just never going to hit the sphere.
So related to this, could you maybe combine with MCMC? If you run it, you start to decorrelate from your initial position, and then maybe prove at some point that you could stop and be exact or very close to exact?
Wait, so say that again? You want to run MCMC first?
If you run an MCMC chain for many steps,
Yeah.
you will decorrelate,
Yes.
and you will basically have an exact sample as well.
Yes.
Sort of almost exact, sorry?
Many steps.
Many infinite steps. But the point is that you get very close to being exact fairly quickly if you traverse from one end of the distribution to the other.
Mm-hmm.
And so could this tool somehow be used to analyze the sample that you're currently having and saying, well, you're exact or almost or very, very close to exact, you should stop your chain reaction?
It's a good question. So I guess in my view, the style of exact sampling that deals with MCMC is this coupling from the past style ideas. I haven't thought about whether we could sort of revisit MCMC with this mindset and try to formulate what's happening in MCMC in these terms. I don't know. It's not obvious to me that that's possible, but it's an interesting problem to think about.
Maybe ask a more high-level question. This came up both in Max's talk and your talk about we all seem to believe that modeling uncertainty is important. But it's also very, very complicated. So I'm wondering more from the Microsoft perspective, this whole infer.net challenge about really trying to bring probabilistic programming to the masses. How is that going? What are the challenges?
Yeah, so I'd say the way I see it is probabilistic programming kind of has two faces. I think one of them is this story that I've pushed here, which is we want the masses to have probabilistic models. And then there's huge challenges, which is even if you solve all the inference things, how do you get people to know what these models mean? How do you get people, the average programmer to write down a meaningful model or a good model? But then there's the second view of probabilistic programming, which is it's just a tool to help the experts build their models faster. So it sort of allows this rapid prototyping of I can add this one extra component and I don't even have to go in and change my code. I can just press go and I'll get back a reasonable answer. And an expert is able to deal with these problems of inference may fail and they can recognize when it is. So there's perfectly good use case for it, which is just improve the productivity of the experts. And I think that's what, I guess if I'm thinking what's valuable to Microsoft, that to this point is what is valuable. So I think, you know, these people who are highly trained in building the inference algorithms can then service or help a much wider group of people by having this unified view.
It's time for lunch and the poster sessions, and then we'll decide what to do after that. Bon appetit.